All right, silly people, here's the situation. What we're trying to do is we are trying to prove that for a particle that is in 1 over r potential, um, uh, that if the particle is making the path of a circle, that at the perihelion it's going to be some distance away from the source of the potential. Um, and if the particle is tracing a parabola instead, that the particle will be half that distance at perihelion. So uh, we're going to be doing this using this equation here, which is given in Goldstein uh, for general Kepler orbits with eccentricity e and perihelion angle theta prime. Um, Also, both of the particles have the same angular momentum, so that's a useful thing. So for a circle, I'm gonna. By the way, for both of these, I'm gonna have theta prime equal 0. That's just a dummy variable that you can put anywhere. I'm making it 0 for prettiness, um, which means at perihelion we're looking at the bits where theta is equal 0 as well. Okay, so for the circle, the eccentricity is 0, which means this equation will just be, I'm going to call it 1 over r naught is equal to mk over L squared. So r naught is L squared over mk. All of those factors are shared with the other um, particle, so I don't feel bad leaving it like that. R naught is L squared over mk. Then for the parabola, the eccentricity is equal to 1. We are evaluating at the perihelion, so theta is 0, so cosine theta is just 1. Um, so the perihelion radius equation, the parabola radius equation at perihelion is going to read mk over L squared times 2, which you can solve for. RP is going to be L squared over 2mk, which means it's 1/2 of the circle radius for the same potential. Cool. That's the easy part. I should have written this for general theta, really. I'm going to go ahead and do that. So 1 over RP will be mk over L squared 1 plus cosine theta, which means in general, RP is going to be R naught divided by 1 plus cosine theta. Okay. So the next bit of this problem is asking about what if, like, for any particular point in the system, whenever the objects are moving, uh, what is the relationship between the circular orbit velocity and the parabolic orbit velocity? In general, you can write the velocity for one of these particles as being square root r dot squared plus r squared theta dot squared. Well, for a circle, that's real easy. R dot is equal to 0, so the V naught, I'm going to call, is just square root of r squared theta dot squared. That's r naught squared. So it's just r naught theta dot naught. I'm going to have to differentiate between the two different theta dots because they're not necessarily the same. The only thing that they share are angular momentum and the potential. So let's put it in terms of that stuff, shall we? Um, okay, so R naught. Let's use the definition of the angular momentum now, which is going to be mr naught squared theta dot naught. Okay, let's solve that for theta dot. So we have ml over mr naught squared is equal to theta naught dot. So plugging that into the formula for the circular velocity, it's going to be L over m r naught. Okay. Do we want to take that a step further? Sure. We already know what r naught is in terms of L, m, and k from up top. So we can also plug that in. So we'll have L over m times L squared over mk. The L will cancel out, so will the m. The k will move up top. So it's just k over L. Okay. So we have to prove that the velocity for the parabola at any given point is that times root 2. So we're gonna give it a good college try. I'm gonna use this equation again, and I'm gonna do time derivatives on it. Bam. Okay. First by just inverting it. So you'll have RP is L squared over MK times 1 over 1 plus cosine theta. And so RP dot will be del RP del theta theta dot. It's going to be L squared over MK. You're going to have a sine theta theta dot up top and a 1 plus cosine theta squared on the bottom. All right. What's cool about this is that it shares a lot of factors with RP anyway. So we'll rewrite it now as RP times sine theta theta dot divided by 1 plus cosine theta. So the velocity of the parabola at a given point will be RP dot squared plus RP squared theta dot squared. Using this definition of RP dot, we can expand this to be RP squared sine squared theta theta dot over 1 plus cosine theta squared. It's supposed to be squared as well. RP squared theta dot squared. Awesome. So both of them have a factor of RP theta dot, which we can factor it out. And then I'm also going to go ahead and expand, or I'm going to go ahead and make the 1 term into a 1 plus cosine theta squared over itself term. Right? And then factor out the 1 plus cosine theta. And then inside the radical, you'll still have sine squared theta. I'm going to expand the squared term, so it's going to be 1 plus cosine squared theta plus 2 cosine theta. So you'll have rp theta dot over 1 plus cosine theta times the square root of 2 plus 2 cosine theta, because sine squared theta plus cosine squared theta is 1. Now you can factor a 2 out of the radicand, so root 2, and now you have the square root of 1 plus cosine theta over 1 plus cosine theta, which simplifies to just having the radical on the bottom. Okay. Now, we want to put this into terms which the two different particles share. At this point, it's worth mentioning that theta dot has been theta dot p this whole time, because the angular velocities are unique to each one. So if you use the definition of angular momentum, you'll have mrp squared theta dot p. And solve that for theta dot p is going to be L over mrp squared. So now you're looking at having a Vp equals root 2 over root 1 plus cosine theta times L over mrp. Now this is kind of funky. We do have a certain relationship between rp and L and m and k and 1 plus cosine theta. I'm just going to plug in that relationship. It's this one up here. Whoa. It's this one up here. So now we're looking at, I'm just going to copy that down actually. Instead of plugging this straight in, let's just solve this for L. All right, so L will be mkr p times 1 plus cosine theta, all under a radical. Pretty gnarly stuff. Okay. Plugging that in on the velocity term, the thing actually cancels out. Yeah. So now you just have root 2 times square root of mkrp over mrp, which translates into having a root 2 k over mrp. Okay, so what I didn't realize is that one of the things that is said in the problem is that the two particles are passing through the same point, um, which means Rp is equal to R in this case. Rp is equal to R naught in this case. So looking back at this thing, this L over M R naught, this V naught is, so looking back at this thing, this V naught is equal to K over L. If we put that stuff in there in terms of the radius, so I'm talking about saying R naught is equal to mk over L squared, no, L squared over mk. Yeah. And solving for R, so no, solving for L, talking about mk R naught, just square rooted mk R naught, and then plugging that into this thing, so V naught is equal to k over square root mk R naught, and then simplifying that into just one radical of it's k over m R naught. Compare that with what we got down here. We have 2k mr, so Vp is equal to the square root of 2 times V naught